All right, let's cover Unit 6, which is thermochemistry. This will be a rather big unit, much like the solutions unit, and it will be pretty tough if you're not up to par with our standards on thermochemistry, but I got you through this unit. We are going to start with this question here to start your brain back up and get ready to go straight into thermochemistry. When detonated, delta H of nitroglycerin is found to be negative 5,720 kilojoules per mole. Is this an exothermic or endothermic process? Would this be located on the reactant or product side? All right, so if you recall, the nitroglycerin blowing up, so detonation, is producing this much heat per mole. Negative 5,720, especially the negative, represents that heat is being released. In other words, heat exits in very bold letters. Is this an exothermic or endothermic process? Well, we know it is exothermic because if you recall my other videos on thermochemistry, we know that when heat exits, it's related with exothermic. Therefore, the detonation of nitroglycerin is exothermic. Let's do that in a different color. All right. Would this be located on the reactant or product side? Well, this is asking about our equation. So for every equation in chemistry, we are going to have like, if I give you an example that has nothing to do with this, we're going to have like Na plus Cl produce N NaCl. Basically, it's saying that when detonating, it's going to have an equation like this. So will the equation be on the left-hand side, which is left-hand side of the arrow, which is the reactant side, or the right-hand side of the arrow, which is the product side? Well, we know that from our previous discussions on thermochemistry, when heat is exothermic, the sign is negative. Therefore, the negative value for delta H is always going to be found on the right-hand side, meaning that it will be on the product side. So if we have, say, nitroglycerin as Z, it'll produce something like x plus y. This probably isn't accurate at all. I'm just giving an example. And we will have negative 5,200 or 700, negative 5,720 kilojoules on the right-hand side of the equation. Moving on, let's try to go through question 2. All right, 50 grams of water started at 23.2 degrees Celsius. The final temperature of the water is 27.6. So we already know that, let's scroll up a little bit. We have our initial T I initial, temperature initial, and we have the final temperature as 27.6. How much heat was required? Heat unit is always Q in chemistry, and it gives us this C value. If you recall from our previous thermochemistry unit, we know we're solving for Q. That means we have to look for an equation that we know is going to give us Q. If you look on the front of your study guide, you're going to be given the equation Q equals mc delta T. Luckily, this equation is given to you, so no need to memorize. But Q is going to be our heat, and we are using mc delta T, mass, C, the specific heat capacity, and change in temperature delta T to solve. Let's figure out delta T first. Delta T is going to be final minus initial. And we have our final here and initial here. So moving here, delta T is going to be equal to final 27.6 minus initial 23.2. Subtract both of these and you're going to get 4.4 degrees Celsius for your delta T. Now we can solve for Q, heat. We have mass, 50 grams. We have C, specific heat capacity, or right there, 4.18. And we have delta T we just found as 4.4. All right, multiply all those three numbers together, and you are going to get 919.6 joules. And that is our final answer. Not like the boxes today. Okay. Question 3. What is the specific heat or the specific heat capacity C of gold if 208 joules of heat comes off Q from 95 grams M from 10 degrees Celsius to 33 degrees Celsius? We know that 10 degrees Celsius to 33 means that 10 is going to be our initial and 33 is going to be our temperature final. Calculate delta T. Delta T equals final minus initial, 33 minus 10 gives us 23 degrees Celsius as our delta T. Solving for Q equals mc delta T, we know that we're looking for C. Q is 280 joules, equals mass, 95, given here. C, we don't know. And delta T, we know, we just found was 23. All right, so we will have 280. If we see this, we multiply these two, and we get 280 equals um, 2,185 C. So if we're solving for C, we divide 2185 on both sides, and we get C equals 0.128, and our unit for C, specific heat capacity, is always going to be, or in this scenario, since we solved with joules, is going to be joules per gram times degrees Celsius. And this is our final answer. All right, let's try number 4. The peanut bag claims that their peanuts contain 4.9 calories. When you perform the calorimetry experiment, you calculate it to be 3.1 calories. What is your percent error? Percent error, you are not given this, unfortunately. Not given. Percent error formula is going to be the absolute value of your actual minus experimental over actual times 100. In this scenario, our actual value is going to be 4.9 since they claim that they contain on the package. So we're going to use this as our actual, and you calculated in your experiment as 3.1. So we know that 4.9 is going to be the actual, 3.1 is going to be the experimental. With that information, we set 4.9 minus, that's a horrible 9, 4.9 minus 3.1, absolute value of that, divided by 4.9 times 100. Solving for this will give you 73% is your percent error. And that is your final answer. All right, let's try number 5. Consider the following reaction of carbon disulfide being produced from natural gas. And it gives us this equation and kindly our delta H. What is the delta H RxN, or the change in enthalpy? And you can also call this the heat of reaction. So let's just write that somewhere else. Delta HRXN equals change in enthalpy, or the heat of reaction. And RXN is an abbreviation for reaction. So it asks us, what is the delta H RXN when 2.5 grams of sulfur is reacted with excess methane? We got to use dimension analysis to solve for moles first. Therefore, and convert that moles using our conversion factors from our equation here and our delta H to find the delta H RxN. The molar mass of sulfur, molar mass, is going to be 32.7 or 32.07 grams per mole. And we can go ahead and ignore excess methane because sulfur is reacting with the excess methane, not the other way around. So with this given information, we always start with our given 2.5 grams of sulfur. For every 32.07 grams of sulfur, we're going to have 1 mole of sulfur. All right, so based on our stoichiometry experience, we know that for every 4 moles of sulfur, 4 mole sulfur, we're going to have 1 mole of the whole reaction. Basically, this means that for this one reaction to take place, we need 4 moles of sulfur. And if we have 4 moles of sulfur, we can have 1 mole of the reaction. That is the special part about the thermochemistry dimensional analysis. And so for every 1 mole of reaction, we get the delta H of negative 106 kilojoules. Basically meaning that for every 1 mole of reaction that takes place, one reaction, we produce that much delta H heat. Or sorry, change in enthalpy, which is basically, it means that it's the measure of how much heat enters or exits the system. So very fancy words for not so fancy definitions. Calculating all the top ones, multiplying together, and dividing by all the bottom ones, you are going to get your final answer of negative, because we have a negative on the kilojoules, 2.07 kilojoules as our delta H RXN, which is our final answer. All right, let's try number 6. How much heat in kilojoules is associated with the production of 283 grams of water? And it gives us this almost the same equation as before, just different elements, compounds. So it even gives us delta H, which is very kind, and it simplifies our process a lot more. So we're looking for the amount of heat, which is in kilojoules, because it specifies that they want it in kilojoules. All right, so for this one, we're going to solve for the same process as before. So using our dimension analysis, we start with a number that we're given, 283 grams of H2O. And we have to know that the molar mass of H2O is going to be, there's H2O, if we have two H's, 1.01 plus 1 of our oxygens, which is 16, we're going to have 18.02 grams per mole of H2O, the molar mass of H2O, molar mass H2O. All right, so there's, for every 1 mole of H2O, you're going to have 18.02 grams of H2O. And for every, look at our equation, we have 2 moles of H2O. There, we're going to have 1 mole of the reaction. For every 1 mole of the reaction, we're going to have our heat value of negative 890 kilojoules. We know everything cancels, as we specified in many dimensional analysis problems, and we are left with kilojoules, letting us solve. Multiply everything on the top, click enter, divide by everything on the bottom, and that will give you negative 6,988.62 kilojoules as your final answer. And that is it. All right, moving on, we have one more page of stuff to get through for our thermochemistry unit. So, number 7 says, the following diagram illustrates both temperature changes and the phase changes, which is solid liquid to gas or gas to liquid to solid, that occur as you add heat to a substance. So, as you know, if you add heat to a solid, it's going to become a liquid. If you add heat to a liquid, it's going to become a gas. So each portion of the curve is labeled from A to E. Actually, the A got cut off, so we're just going to put that in here now. That occur, blah, blah, blah. Answer the questions below concerning the diagram, yada, yada, yada. Okay. So, A, which portion of the curve responds to boiling? Boiling is the process of vaporization, which means that you're going from a liquid to a solid, or sorry, liquid to a gas. So if you boil water, you go from liquid to steam, which is gas. And so let's label these, these little lines on the graph. So on this point B, we're going to have our first transformation, solid to liquid. On the second flat line, we're going to have our second transformation of liquid to gas. A is going to be solid, and this part here is going to be liquid, and this third part here is going to be gas. So liquid to gas is going to be this right here, which means that it corresponds with the letter D. E. Which portion of the curve corresponds to heating the gas state? Heating the gas state means that you're getting your gas and heating it even further. This area here is your gas, and by moving it upwards, you're heating it even further. Therefore, it is E. Which portion of the curve corresponds to the solid phase only? So out of everything here, which one is your solid? That's right. Right here, it is going to be A. Is the process going from point 1 right here to point 2 right there exothermic or endothermic? Well, we know that the further you go up on the scale, the more endothermic you have to be, because if heat enters, you have to have heat entering in order to actually go from a liquid to gas. So from stage 1 here, the line 1, where we have our first transformation from liquid to gas, and our stage 2 where we are a gas, we're going to gain heat in order to become a gas. Therefore, it is endothermic. Let's write a little explanation, even though it says just circle. You're gaining heat from liquid to gas, endothermic. So endothermic, En, heat enters. All right, let's try E. This is our last question of the unit, and it is the longest. And it is probably one of the most uh, complicatedly stupid things we have to do in this unit. But on our final, everything is multiple choice, and it's only worth, 1 point. So if you're missing something on the thermochemistry unit, just miss this one, and it's not too big of a deal. But I'll still teach you how to do it. So number E. What quantity of heat is involved in the process of converting 250 grams of steam at 110 degrees Celsius to liquid water at 57.5? And make sure your answer has the proper sign, blah, blah, blah. It's not a one-step calculation. So this is kind of important. This is not just a Q equals MC delta T type calculation. You're going to go various steps in order to calculate this. And as you can tell, we have a lot of given things, which means that our equation is going to be very long. All right. So for these types of questions, when they ask us the quantity of heat and it gives us all this whole bunch of temperature stuff, draw one of these phase change diagrams. So I always like drawing these. I'll draw it in black right here. We have our phase change diagram. It doesn't have to be anything fancy. It just has to get the job done. We have 100 degrees Celsius here. We have on this line right here 0 degrees Celsius. So this is our solid, liquid, gas. This is solid to liquid. This is liquid to gas. All right. The same graph that we covered in the question before. So we're going from 110 degrees to 57.5. So we're going from, let's say this is 110 degrees Celsius. We're going to 57.5 degrees Celsius. So we're moving. So let's just draw one arrow here, and one arrow here. That's 3 steps. That means we are going to have 3 separate equations we're using. And if we're losing heat this way, that means our we got to calculate each of the specific delta T's, and all of them will be negative because our overall change in heat is going to be a loss. And that a loss means that heat is exiting, which means that it's endothermic, which means that your answers are all going to be negative. Okay, so that was a lot of information, but I trust that me solving this will answer all the questions. So let's calculate delta T for this segment here. We learned in our previous unit and time in our thermochemistry unit that this is one step, so you have to have separate delta T's for this. And if you're asking about this part right here where it's completely flat, if there's no slope, there's no heat change because this bottom x-axis heat added and this top axis is going to be temperature in degrees Celsius. So with that information, we know that we have to calculate delta T for this part and delta T for this part. So delta T is going to be in final minus initial. Delta T equals final minus initial. Our final temperature is going to be 100 degrees Celsius. Our initial is going to be 110 because we're moving downwards, right? So 100 minus 110 will give you negative 10, and that's in degrees Celsius. Same logic for this. We're going from 100 to 57.5. So this is our initial, this is our final initial. There we go. So 57.5 minus 100 will give you your delta T for negative 42.5 degrees Celsius. All right, so we gotta calculate the first step. Let's do this one as first step, this one as our second step, this one as our third step, because we're moving down in that order. All right, so let's take a look at first step. We're going to use Q equals mc delta T because the line has a slope, which means that there is a change in temperature. We're solving for Q for all of these, by the way. We have M, mass. We have 250 grams. We have C, which is one of our constant that's given right here. So there's three types of C's, one that's a solid, one that's a liquid, one that's a gas. So I say here is solid. We'll just make a note of that there, solid. But in this scenario, we're at the gas phase because we talked that this was the gas, this was the liquid, and this was a solid. So we have to use the C for gas, which is 1.9. Next, we have our delta T, negative 10. And multiplying all that together will give you negative 4,750. And the unit for this is going to be joules because our C is joules. Unit is joules. All right. So the second step is going to be calculating for this part right here without the slope. Since there is no delta T, we can't use Q equals mc delta T. So we have to solve using dimensional analysis. So we start with 250 grams of steam. 250 grams of steam. Steam is basically water vapor, so we know it's H2O. And for every 18.02 grams of water, H2O, that's the molar mass. Let's just write that there. This is H2O. So the molar mass equals 18.02 grams per mole. That is our conversion factor we're using here. So for every 1 mole of H2O. And in our process of quantity of solving for quantity of heat, we know that every 1 mole of H2O, since it's just water, it's just 1 mole. 1 mole of H2O, there is going to be, and we have to use our delta H fusion or delta H of vaporization. In this scenario, we're going to use the delta H of vaporization because we're going from here to here. So this point right here to this point right here. So this is, as we've talked about, liquid to gas. Liquid to gas is called vaporization, hence the VAP representing vaporization. If we were to have our equation down here, we would know that solid to liquid is called fusion. Therefore, we have to use delta H FUS. In this scenario, we're going on the top, no slope bar, so we know that we're using delta H VAP, vaporization, 40.7 kilojoules, and that's per 1 mole of our H2O. Solving for this in the end will give you 564.65 joules. But we have to, for dimensional analysis, the trickiest part is we have to remember that this joule value is negative. We have to put the negative manually, which is very annoying, and you're bound to forget once at least when you're doing chemistry. And so we have to match our negatives because this is an exothermic process. As you move upwards, you're gaining heat, so heat enters. But since we're moving downwards and canceling the heat off to make it liquid water, we are in the process of exothermic. Exothermic delta H values, or heat values in general, are negative. Therefore, this negative has to be present. Finally, the third line, we have a slope, so we can use Q equals mc delta T. And as you probably know the drill by now, the mass is 250. The C value this time, we've gone from a gas to a liquid. So now we're in the liquid phase because this whole thing right here is liquid. We have to use our liquid value of C, which is 4.18, multiplied by our delta T value, which we found here for this specific part that we're looking at. as 42.5 degrees Celsius. So in our Q equals MC delta T, we know that the change in temperature is negative, so we don't have to worry about the negative. But the reason why we had to worry about that in our question, step 2 was that, it's dimensional analysis and we have our delta HVAP values, so we have to put the manual negative in there. Multiply these three numbers out as we've done before, and you're going to get your answer of negative, oh, that's a big number, negative 400,000, wait, sorry, negative 44,412.5 joules. So we take these three numbers, and since we're looking at the quantity of heat, the total quantity of heat involved in the process, we're looking at the heat involved in step 1, the heat involved in step 2, and heat involved in step 3. So we have to add these three numbers together. Let's do that in a different color. There's a lot of stuff. So we have this one, and this one. So our total quantity of heat, Q, is going to be step 1 plus step 2 plus step 3. And this is going to be negative 4,750 plus um, parentheses plus negative 564.65 plus negative 44412.5, which is going to give us in the end negative 49,727.15 joules, or if we wanted to use kilojoules, we would divide that by 1,000 and we would get 49.73 when we round this to kilojoules. And that is our final answer. And so that is it for thermochemistry.